Are you okay to start if I introduce you?
Yes.
Okay, thank you. Okay, so the next speaker is Leticia Pardo Simón, who's at IMPAN, and she's talking about entire maps with Cantor bouquet Julia sets.
Thank you, Gwyneth. And also thank you to the organizers for their effort and for giving me the chance to tell you today about transcendental entire maps with Cantor bouquet Julia sets. And this is work in progress with Lasse Rempe. So just to set some notation. So today we are going to be talking about transcendental entire maps, iteration of these maps. And instead of focusing on the Fatou set, like in the previous talk, we are going to try to describe the Julia set of some of these maps. And we are going to do so by looking at their escaping set, which I remind you is the set of points that escape to infinity under iteration. And we are going to denote it by I of f. And one of the reasons why we do this is because I remind you that Julia set is always the boundary of the escaping set. So already in 1926, Fatou observed that the escaping set of certain functions in the sine family contain some arcs to infinity. And 60 years later, Devani, in a series of papers written with different co-authors, observed analogous curves, this time belonging to the Julia set of maps, certain maps in the exponential family. Like, for example, here in this picture, we have, I think it is e to the z minus 2. So the Fatou set of this map is depicted in blue, and it is the attracting basin of a fixed point. And in black, we have what seems to be a collection of these arcs to infinity. This picture goes, imagine it goes far to the right. And two of these curves are drawn in yellow. And these curves are known as Devani hairs or dynamic rays. Now we just don't see some curves, but it looks like, or the picture might indicate that these Julia said this collection of curves have some kind of topological structure, and this is the case. So to give you the next result, I'm going to define what we mean by Cantor bouquet, by a Julia set being a Cantor bouquet. So we say that the Julia set of a function is a Cantor bouquet if every connected component of the Julia set is an arc to infinity that we call hair, and if the Julia set is topologically straight. And by this, we mean that there exists a homeomorphism of the plane such that the image of every hair of every of these curves under this homeomorphism is a straight horizontal line. And with this definition, in 1993, Arts and Overstegen showed that for maps in the sine family with lambda between 0 and 1, and in the exponential family for mu between 1 and 1 over e, that is, whenever we had this, the Fatou set being an attracting basin, then the Julia set was a Cantor bouquet. So we know it's a collection of curves, but besides, we also know how these curves sit on the plane. So let's look at more functions with these dynamic rays. Let's start by this. So in today's talk, we are going to adopt the following terminology introduced by Anna Benini and Lasse Rempe recently. So we are going to say that a function is quiniferous if for every point in their escaping set, there is some iterate of the point that we can join by a curve to infinity, gamma n, such that the f maps injectively to yet another curve to infinity. This time joins the next iterate, and such that the minimum of the modulus of the points on these curves, gamma n plus 1 and so on, tends to infinity. So in particular, these curves are in the escaping set of our function. And an observation is that whenever a function is quiniferous, then every point in their escaping set can be connected to infinity by a curve of escaping points. This is because this definition tells us that we have the point set, and we look at some iterate, it's going to be joined to infinity by such a curve, and then taking pre-images of this curve, we are going to be able to find this curve that joins it to infinity. Now, why we need to take some iterate to satisfy this definition? Well, note that this curve might contain some critical value or critical point, and then we might have this kind of structure, so the image would not map injectively. But the point is that some iterate will be mapped to such a curve. So I want to give you some examples of quiniferous functions, but first let me remind you that the singular set of a function plays an important role on its dynamics, and it's been defined already, but just it's a bit late. So let me recall that the set of singular values is the smallest closed subset of the plane where our map fails to be a covering map, or equivalently, the closure of the set of asymptotic and critical values of f. And for the rest of the talk, we are going to restrict ourselves to the well-known Menko-Liouvitch class, denoted by B, which consists of all transcendental entire functions for which the set of singular values is bounded. And for these maps, in particular, we have that the scaling set is contained in the Julia set. So now, which functions do we know to be quiniferous? Well, in 2003, Schleicher and Zimmer extended the Vanis results to all maps in the exponential family, and also all maps on the cosine family are quiniferous. And more generally, functions of finite order of growth in class B are quiniferous. And let me remind you that a function has finite order of growth if the logarithm of the modulus of f of z is a big O of log of the modulus of z. So in other words, a function has degree d if it grows like e to the z to the d. And just for the record, in this same paper of Bracket-Rutten, Fusser, Rempe, and Schleicher, quiniferousness, so the family of functions that are shown to be quiniferous is bigger, and I'm going to denote it by BRRS, and these are those that satisfy certain growth conditions and some geometric properties that are not relevant for us. We just need to remember that there's this class which is bigger than this one. So of course the exponential and cosine families belong to this, and then functions of finite order are inside this class. Now note that not all functions are quiniferous, and in this same paper we just mentioned, the authors construct a function in class B for which the Julia set, and therefore the scaling set that is contained, contains no arc. So the function is quite far from being quiniferous. And more recently, Lasse also has a paper where he shows that for some functions for which the Fatou set is connected, and we will define in the next slide, the connected components of the Julia set together with infinity, instead of being arcs, might be other types of arc-like continua, like for example, an Aster continuum, or also known as bucket handle, or the topologist sine curve. And well, just mentioning that instead of looking at curves, one can look at another connected sets of the scaling set known as dreadlocks, and this has been developed recently by Anna and Lasse for functions for which the forward orbit of the singular set is bounded. But in this talk, we're interested in quiniferous maps. So leaving that aside, we're interested on one hand on quiniferous maps, and on the other hand on functions for which the Julia set is a Cantor bouquet. So let's start by generalizing the maps, the exponential and sine maps we mentioned before that had this Fatou set that was an attracting basis. And we define an entire function to be of this joint type if it belongs to class B, if it has bounded singular set. And moreover, every point in the singular set tends to an attracting fixed point of f under iteration. And this is equivalent to saying that the Fatou set is connected. And moreover, that the forward image of the singular set is perfectly contained in the Fatou set. Now, why are these functions important? Well, to start with, whenever we have a function in class B, if we multiply this function by lambda for some complex number, and the modulus of this lambda is sufficiently small, then the function lambda f is of this joint type. And it turns out that lambda f and f are in the same parameter space, which means that they are quasi-conformally equivalent, which means that there exist quasi-conformal maps C and phi such that we have the relation lambda f equal f composed with phi. And thanks to this, we have, by a result of Lasse, that the dynamics of lambda f and f are related near infinity by a certain analog of Botch's theorem, let's say. So we don't have Botch's theorem near infinity like we do for polynomials, but still we can relate the dynamics of these two maps in subsets of their, by a conjugacy in subsets of their Julia sets. And this is an important property that we will use later in the proof of the results. So now with this definition, Arden over Stevens' result generalizes to some disjoint type functions. More precisely, in 2012, Baranski, Jarque, and Rempe showed that if we have a function in class B of finite order, and that is of this joint type, then the Julia set is a Cantor bouquet. And let me remind you that we said a few slides ago that these functions are quiniferous. And even more generally, they prove the result to hold for these functions in this bigger class mentioned before. So our first goal, the goal of the work we are doing, is to understand the relationship between quiniferous maps and Cantor bouquet Julia sets. So when we restrict ourselves to these joint type maps, if the disjoint type map in question has a Cantor bouquet Julia set, then the map is quiniferous. This is because, by results of Lasse, all points that are not all points in the hairs of the Cantor bouquet, but maybe the endpoints, need to escape to infinity. So in particular, the function is quiniferous. Now, the theorem in the previous slide suggests that when we have a disjoint type map which is quiniferous, then the Julia set is a Cantor bouquet, or at least this is what Baranski, Jarque, and Lasse proved for the maps that we knew that have dynamic range. But our first result says that this is not the case. So we've constructed a function in class B that is quiniferous and of disjoint type, so that the Julia set is a collection of arcs. But however, the Julia set is not a Cantor bouquet. And to explain you how we get this, I need to give you a definition of a Cantor bouquet for a subset of the plane. So before I defined it for Julia sets, using that the definition was slightly easier because we are using the properties of Julia sets. But now we are going to use the following characterization that appears in a paper. I think it is 2015, but I'm not sure. Nada last. So we say that the subset of the plane is a Cantor bouquet if the following hold: if the set is closed, if every connected component of the set is an arc that connects a finite endpoint to infinity, if for any sequence of points that converge to yet another point y, the arcs y and to infinity converge to y infinity in the Hausdorff metric. So we want all the arcs to be nicely converging to any limit arc. Then we want the endpoints of X to be dense in X. And we want that the only points that are accessible from the complement of this set are the endpoints of X. And this is equivalent to saying that every hair of X is accumulated by other hairs from both sides. So now if we consider disjoint type and quiniferous maps, let's see which properties we have directly or were known before. So of course, the Julia set is always closed. Every connected component of the Julia set is an arc connecting a finite endpoint to infinity. This followed from results of Lasso on disjoint type functions. The endpoints of the Julia set are dense in the Julia set. This is because we've said that the only points that might not be escaping, in particular repelling periodic point, need to be endpoints. So we have there that. And that every hair is accumulated by other hairs, again, by results on disjoint type maps. So we knew these properties. So the only property that we needed to check whether it holds or not is this nicely convergence of hair or of the hairs. So our question was, is it possible that we might have some hair of the bouquet? And this was supposed to be a straight line, wait. Is it possible that we have some hair to which we have other hairs accumulating, but let's say with hooks, for example, and therefore it wouldn't converge in a house of metric. And this is what we do. This is what we, how we prove our theorem. We construct a disjoint type map with these kind of arcs in their Julia set. And just for a moment, how we do this? Well, yes, for those who know these definitions, we design some logarithmic tracks. They don't really look like this, but the point is that they get thinner and thinner. They get thinner so that we do get that the function has arcs, not other Julia are like continua, for example, like we said before they could have. And we make sure they have hairs. We have the tracks themselves have these hooks. We do the construction in a controlled way, so that when we take the preimages of the arcs that are going to be in here, if we construct it so that there is a fixed hair in this tract, well, they are going to accumulate to a pair of points with the hooks we want to. And when this happens, when we have these kind of points, A and B, such that A is before B, in the sense that it is B is between A and infinity in the arc. And moreover, we have these sequences of points AN converging to A, and then points BN converging to B, such that we have it the other way around. So BN is before in the array than AN. Then we say that this is a bad pair. And I'm mentioning this because I will reference this in a moment again. So this is like very roughly speaking how we get this theorem. Now I want to give you a couple more of results. So in order to do this, we need to define what we mean by an absorbing set of a Julia set. So we say that A is absorbing if it is forward invariant, if for every escaping point some iterate lands in A, which is the same as saying that the escaping set is containing the backward orbits of A. And moreover, we want that if we have some arc to infinity in A, then the image of this arc, which is in A, is also an unbounded arc. With this definition, we prove the following theorem. So if we have a function of this joint type, it is the same to ask this function to have a Julia set that is a Cantor bouquet, than saying that the function, the Julia set contains a Cantor bouquet, which in turn contains all points in the Julia set whose forward orbit never meets a disk of radius r. So, and again, and this is equivalent to saying that there is an absorbing Cantor bouquet in the Julia set. So the most surprising one is this. So the moment, this theorem is telling us, the moment we have an absorbing Cantor bouquet, a Cantor bouquet in the Julia set to which all escaping points are mapped, then automatically the whole Julia set needs to be a Cantor bouquet. In contrast to the other theorem that said that we can have arcs and may not have a Cantor bouquet. So this implication, A implies B. This follows from some results in my PhD thesis that says that whenever we have a Cantor bouquet and this joint type map, and we have this kind of set, we can always project the Cantor bouquet in a continuous way to this set. And therefore, we have the image is a Cantor bouquet. Now, this implication is trivial. B implies C, since, well, any escaping point needs to eventually land in JR of F for any R we fix. And then how we proved C implies A, this is using this notion of bad pairs I was mentioning before. So what we want to prove is that if we have an absorbing Cantor bouquet, we cannot have any bad pairs, because, well, the moment we have a bad pair, the Cantor bouquet is no longer, the Julia set is no longer a Cantor bouquet, as we saw before. So the point was to prove the moment we have this and all escaping points are there, if we assume we have one bad pair, what happens is that we have to have bad pairs everywhere in a rough sense. And this is what makes us have a contradiction. So this is how C implies A. And to conclude, I want to give you an application of these results. So in my PhD thesis, with another purpose, I introduced the following class, subclass of B that I denoted by CV, and consists of all F in B, such that the Julia set of the maps of this joint type in the parameter space, that is J of lambda F for lambda modulus small, we said this is this joint type, have a Cantor bouquet Julia set. So any F for which the disjoint type map in the parameter space, or one or implies all of them, has a Cantor bouquet Julia set. And it is not difficult to see, and this follows from the result of Baranski and Lassen and Xavi that I mentioned before, that these maps BRRS, which I haven't given you the definition, belong to this class. And what I proved is that the maps in this class are quiniferous, which is nice because we don't need it. We don't need this geometric condition, this uniform head start condition that might be difficult to, at least for me, to work with. So the problem, one objection that one might have with this definition is that, well, it is given in terms of a property, not of the map F, but of the map J of the map lambda F. So it's not ideal. So from the results I've announced today, we can get a new characterization of the maps in this class as those for which the Julia set contains an absorbing Cantor bouquet. And we obtain this result by combining this conjugacy that I've told you that there exists between F and lambda F near infinity, together with the fact that for these joint type maps, having an absorbing Cantor bouquet was equivalent to having a Julia set, a Cantor bouquet Julia set. And just to conclude, and this is really work in progress, we are constructing a function. So it's it followed from no results that this class of map belongs to CV, but in this work we're doing now, we are also providing an example of a class of a map in this class CV that does not satisfy a uniform head start condition. So the class CB is strictly bigger than the previous one. And this is what I wanted to tell you today. So thank you for your attention.